in such a space, what ellipses? And see, in this question, I'm asking already half a dozen questions already. If you concentrate on, if you focus on, the word focus is always around, any one of these questions, it's a very humble way, because we probably just consider one polynomial equation, maybe cubic equation. And then if you look at the algebraic variety and then try to determine, classify these sets, even one of them, ellipse, then you can publish it at least, let me say, type-3 pure mathematics is no problem. And archival mathematics, they are all third-rate journals now. Originally they were top journals because managing the editors originally contained Hilbert and Congaree and those people originally. Now they are in modern listing, they are in the third class journal. If you can publish in there, I would respect it very much because so this is done. And then how about in metric spaces which are locally finite graphs? The next one, this is why we're doing lots of graphs. There's another graph coming next batch, another graph session. How about locally finite graphs? Of course, finite graphs are all locally finite graphs. These are not good. Oh, for finite graphs, that one is known already. We just characterized it in, not only this one is characterized, but we characterized much more in November last year when I was in Luoyang, China. I was there for 1 month. Not published. Now let us look at examples of bisectors. Have a look at this equation here. Y squared is equal to x cubed plus ax plus b. What if it is called this is the famous elliptic curve, and anything you can talk about, for example, rational points on it, would give you a great advantage in modern cryptography. Muhammad is very interested in cryptography, and even this curve is extremely difficult to study. This is the elliptic curve, y squared equal to x squared plus ax plus b. X, y are both real numbers. For this, it is an example of an algebraic variety, real fine algebraic variety.
I think such curves are also studied by mathematicians like Euler.
Yes. If you replace x and y by w, z, which are complex numbers, then you have a one-dimensional complex manifold or two-dimensional real manifold.
Yeah.
In which we can, and it has coordinates, in which we can ask these questions if it is two-dimensional. If it is one-dimensional, what happens to these geometric sets? You have to really be careful about that. Now, we can not only define bisectors that way, that was Hilbert's definition. You have to understand that these things, I'm not making it up, it's Hilbert. David Hilbert wrote this in one of his papers. Earlier, of course, because nowadays people usually think that, oh, we have to only cite papers in the last 6 years, and then I think that is superficial, in my opinion. I'm citing papers from 18th century in this course. You will see soon. From 18th century. And can you actually, out of your hand, can you prove any one of those theorems now, if I ask you? Those theorems which are done by famous people like Lagrange, Fermat, Legendre, Gauss. So this is a general definition. Let us take any two subsets, not necessarily two actually. Let us take subsets A, B of a matrix with X is distant function rho. Then we can define equidistant set. Sorry, that is big A, big B. Equidistant set E, capital A, capital B. I'm wrong this. E of A, B. To be the set of points in X which are same distance to both, so to those two. Now, in Euclidean plane, You take two bounded subsets and you characterize in this set. Again, if A is equal to B, then we have whole space X. And it doesn't even require that AB are disjoint sets. So especially when AB are bounded compact sets in some space, say function space for functional analysis, I really want yesterday's PhD student to be here. Because this is where we can do some new research. If we take any one of those function space and use the ancient metric in it, and then you take two compact subsets in it, you can even assume that they are disjoint. How do you characterize this? Bisector first, and then how do we, is there anything like, what is the ellipse like? The geometric subset, beautiful geometric subset of that function space, which is called ellipse. What is it like? Tell me, if and only if condition. Isn't that a good paper? Yes. I would say this is a good paper, even if you are in fluid mechanics. This is a good paper because you will get it into high journals. I don't know, because I don't know the answer. So for function spaces, nothing is known about those beautiful, simple geometric sets. Now let us consider this x to be the Euclidean plane, a to be any point in x, and b be a straight line in Euclidean plane. We are not assuming that the point is not on the straight line, but let us assume that it's, for the moment, assume that it's not on the straight line. The b, a is not in b. So it's all outside the screen. I don't know why it was projecting this. Oh, I can actually minimize it. Something is small. How do you? Don't worry about it. I will click it. What is the bisector of AB like? The equidistant set. Mohammed? 1.1 straight line. What is the equidistant set? Your definition. Parabola.
Yes.
So, and I drew it. Nice, because I can draw nice pictures easily in the computer. This. So this point A is F, which is half the coordinate, half of P0. And X equal to negative P over 2 is B, which is a straight line. Then this is this green, the blue curve, which is hyperbola, is the bisector of these two sets, or equidistant set. Therefore, you can say one thing very easily now. Parabola is a bisector. It's a generalized bisector. Parabola fits in this definition. This is a single one that is a straight line in this case. Parabola is a bisector. Now let us go to two-dimensional Riemann space. Two-dimensional Riemann space, you take any 2 points on it. These 2 points A, B are on the surface. And the interior of the surface is not in the space. The space itself is the whole sphere surface, not the ball, not the closed ball. What is the bisector? This drawn, the red line, the gray circle is the bisector. And it is a gray circle. You need to prove this quickly. Because we cannot just point to the thing. I copied it from internet, but this is not from internet. I copied this picture and then show you without telling you why. That's not good enough. You need to really quickly prove that this is the bisector. This is the EAB, small a. Why? Small students can't do it, actually, this thing. This comes to that question. That question which connects the arc length with the second length. So on this surface, you have a property. That property is that if you have 2 arc lengths are equal anywhere, then their subtended second lengths are equal, and converse is also true in this. And therefore, we consider the bisector of 2 points A, B in the 3-dimensional Euclidean plane, Euclidean space, which gives us a plane going perpendicular to the line segment joining them through the middle point. That's Euclid, no problem. And that plane intersects the surface into a great circle.
Yes.
What is happening is that anywhere, if 2 points on the R S2 are same distance to this red, if any point is same distance to those two AB, then if and only if the second connecting that point to those 2 points are same distance. The second, the Euclidean distance is the same. So the intrinsic distance rho AX equal to rho BX if and only if the Euclidean distance rho 2 AX is equal to rho 2 BX. But we have got this great circle by using the Euclidean bisector, which is a plane, perpendicular to the line segment going from the midpoint. Therefore, that great circle is the bisector in S2 of these 2 points. This is the proof. If you didn't understand, I can write it up even. You need to stop me if you don't understand it. So whenever you want to display something from online or somewhere, you need to really prove it. If it is true, if it is false, then you are actually getting punished by someone else's crime. Is that good? What happened to this? So this gives you the proof that this red circle, the red circle is the equidistant set for, I'm going to display much more pictures now. Javid? Well, I will hold this up and let's show you. This is the screen. If you can see, here's the screen, and this is this red line. I have just red gray circle. It goes through the center, therefore it's a gray circle. This plane, the intersection of the plane with the sphere. This gray circle is the equidistant set of AB points. AB. Now next, we have done this one. This you can't see, I think. I will work it on the board this time. Yes. That's fine. I will work it on the board. So let us consider a different space, which is a locally finite graph. We said that all graphs are metric spaces. We didn't prove it actually. So let us consider a locally finite graph, namely the Gaussian integers. Ring of Gaussian integers. Z squared. So Z squared has elements A plus BI, ABI integers. That is why we call it the Gaussian integer. And then it has 4 unit vectors. This we have left as an exercise as well. And not only so, we can write it out. 1 into 1I. If you use the Gaussian integer notation, it's much shorter. Otherwise, you have to write 1, 0, round brackets, negative 1, 0, 0, 1, negative 0, negative 1. And you have this, then this defines the graph, the Cayley graph. So let us show it. Locally. It doesn't matter where the origin is. It doesn't matter where the origin is. Let me fix, because here you can have empty bisectors. But in order not to be empty, we choose it here. So let us, I will bold it. So there will be one point here. This is your A. 1, 2, 3. And then this is a straight line. And we want to work out its equidistant set. Its equidistant set not right. I draw it probably wrong. Oh, it's fine. It's equidistant set, we work it out together. Of course, if you do it otherwise, it will be also interesting. So, if we are looking at on this horizontal line, it doesn't matter where the origin is, I said already. If you look at these two here, there's no point there, right? But how about that point? That point is distant 2 to this set, and distant 2 to that. So this point is on it. Let me use another color. Which point was it? This point.
Yes.
Similarly, this point is on it.
This point.
So these two are on the equidistant set A. This is B. That is A. We are currently working out EAB. Now, how about that point? That point is distant 1, but here, to that one is going to be 1, 2, 3, 4. Not right, not right. This one, 2, and then you have 4. This one, 3, you have 3.
Yes.
So this point is on it.
Yes.
Similarly, that point is on it. After that, if you move this way, it will be too close to that, but too far away from that. If you move that way, it's the same thing. If you move here, it's fine. Because if you move here, to this distance is increased by 1, and to this distance is increased by 1. So from here, you can actually see that it goes horizontal. It goes infinitely in this direction. So we determine EAB. Not only so, we also determine what? Parabola.
Yes.
Because that is the analog of straight line, this is the analog of a point. This is also a parabola in this space. This space is x equal to z squared u. Both E and parabola are determined. It looks like a parabola in Euclidean plane, right? Because in Euclidean plane, the parabola looks like it starts bending, and then as soon as you go far enough, it seems like two straight lines.
Yes.
And here it is bending only for 5 points, and then after that it's straight.
It is actually a straight line, but that is not actually that. That is
Not going like that.
Yeah.
So this is a same and similar and different from the Euclidean parabola on the plane.
Yeah.
The problem is this distance is many mathematicians talk in very dirty language. They call it Manhattan distance. Which I don't like it because it has nothing to do with Manhattan. It is this distance here. Distance given by that. Or it's a L1 distance, you can call it. So this is a parabola and equidistant set in this. And we have not determined this yet, even for this very special space. You can work on it. What if, let me try, I have to draw it again. I have drawn it to Muhammad already, but Muhammad, how did your test go this morning? Oh, afternoon? You have a test today?
Yeah, it was good. You were asking about exam.
Yeah, exam.
Yeah, it was good, very good.
So you went, you took it already in the morning? Okay. So it was in the morning, right?
Yeah.
Okay. So now we do the same space. Same space. We take different subset and point. For example, this is our subset. Let us do it in a more exotic, romantic way. This is our subset, B. And we take a point outside, it doesn't matter where. power A. Then is the parabola also, the equidistant set and the parabola also similar to this one? Now we have this point on it because to this distance is 2, to this distance is 2. So this point is on it. That point is also on it. That point is also on it. How about this point, not that point? 1, 2, 3, 4. 1, 2. So this point is not on it. Where does it go? It's probably going that way.
I think it will move from.
Yeah, it will go that way. So you might have something like a picture like that. It's going that way. So, question. My question is, I don't want to ask conjecture, but determine parabolas. This is nobody published it. Parabola in x z squared zn, let's say u, n any natural number. Here we are looking at n equal to 2. Isn't this a good question? I think so. I always think different from other people. Some people think this is probably not worth doing, but I think it's very, very much worth doing because I don't know the answer. I asked famous people, they don't know the answer either. That doesn't mean that this is a famous question, because famous question must be asked by famous people. I'm not famous. So this is not a famous question, but you can really answer it, can't you? Even by programming for some finite experiments and then try to make a guess, and then after that you must see how to prove it. Is anybody in the audience who are from outside this ASSMS? I heard you're from GC University. I heard that Faisalabad, right? Faisalabad people are trying to attend and no, never came, I think. Okay, I will pass this around. This is published work. Bisector in this space. Pass around. Bisector in this space published in 2019 by my student Ray and myself. He is now in China, working in the university. That can be obtained from, of course I'm going to upload the slides to the group. You see that from this diagram, you see that the bisector is not always the same. It doesn't look the same. Some cases, it spreads out the whole two areas. In one case, it just looks like a straight line. So even for bisectors in, we have actually done for any of these, for any n. That is only n equal to 2 to illustrate. For any n, we have characterized the bisectors. Of course, for Euclidean plane, we are not the first ones to do this. It was actually done by a professor from Romania here in ASSMS, long time ago, with a Pakistani student. He is now in King Fahd University, in Muhammad Imran. Now he is probably called Professor Dr. Muhammad Imran. And his supervisor is Professor Tomescu, John Tomescu. They did it all for plane, for the n equal to 2 case. And they probably also mentioned that it is true for any dimension, but did not write down a proof. We not only did this, in that paper we did quite a lot of other things as well. So this is one of the things which we did. Now here, in this space, for example, in this space, for any n, what are ellipses and hyperbola like? Characterize, you have a paper. I can guarantee. If you have a paper, I will recommend you to submit it to some journals, and they will accept it immediately if you write it nicely. So what are the hyperbola and ellipses in this? It doesn't seem to be difficult. It doesn't seem to be difficult. Now, Of course, there are other questions. What are, if you know the ellipses, you know the circles, right? Because circles are special cases of ellipses where A and B are equal now. 2 points A and B are equal. So the sum of distances become just the diameter because you are adding this radius twice.
Yes.
So if you can, what are the circles here like and how do circles intersect again? So these are 2 other questions. What are the circles? Determine circles. These are geometric sets. And characterize their intersections. Does it have any bearings similar to the Euclidean one? No, actually, come on, not the question. Full stop. So this is a small project, that's a small project. This small project probably will entitle you to a PhD if you are after that degree. You can even use a deep learning to do this. Now, this is the batch 6. Now we will move into batch 7.
Professor, should I raise the board?
Sorry?
Can I raise the board?
Thank you. Can you, if you want to take picture, you can take picture. And now we go to batch 7. Now this computer is also here, so let me just turn it off. Does it turn off itself? Any questions or comments or discussions? Please actively process this thing. Don't just leave it in this room. If you process it, you will like it. I think I liked it very much in the last 30 years. I like this kind of study very, very much. So it's not turning on, so it's fine. It's not mine. The next one is we are going back to graphs again. And I'm going to talk about that between the concepts. Any questions or discussions? I have proposed too many questions even in the last hour. The main question is the question 1. And goes about Riemann services and locally finite graphs, especially in particular this kind of graph. Now, there's something very interesting is going to still come from graph theory. And many people didn't like this mini course because too many graphs theory, too much graph theory. But it is because, in my opinion, this is giving us ideas, so this is the right thing. So in this batch, it is a concept of the graphs defined by distances. Graphs as metric spaces by distances. Which means that we're going to have a matrix